we do u1 times v1 plus u2 times v2 plus u3 times v3, so on and so on, all the way till we get to the end, un plus un times vn. Why is that surprising? Why is that a surprising way to define a product of two vectors? Well, look at the result. What kind of object is this? It's a number. These two things are numbers. When we multiply them, we just get a real number plus another real number all the way across. When we add all these up, that's just a single number. So you multiply two vectors and you just get a number out. So you don't even get a vector back when you multiply two vectors with a dot product. So this is sometimes called the scalar product for that reason, that the result is a scalar. It's a real number, a constant. Those are all different ways of saying the same thing. So for slightly different notation and maybe a little bit more concise notation is we could use summation notation or sigma notation and just write this like this. So we sum up all the components from 1 to n, the products of those components. So if you're comfortable and familiar with sigma notation, this is one way to write it. I personally actually prefer this way up here because it's a little bit more informative, I think. It's a little bit easier to see just right away without interpreting the sigma notation. Anyways, that's that. Let's do an example. So if we have u is equal to 1, -2, and 5, and v is equal to 4, 3, and 1. So what is this dot product? Well, we just do exactly what it says. 1 times 4 plus -2 times 3 plus 5 times 1. So we get 4 minus 6 plus 5. That looks like 3 to me. So maybe what I should have written was this is u minus v, or sorry, u dot v. U dot v is equal to this. We're taking u1 times v1 plus u2 times v2 plus u3 times v3, and then we're just simplifying the numbers, and it comes out to 3. This maybe seems a little bit bizarre, but we'll see in the coming videos why this dot product is really useful. See you then. So if you've been following along so far, you may have noticed that we haven't talked about multiplying two as 3 times v3, and then we're just simplifying the numbers, and it comes out to 3. This maybe seems a little bit bizarre, but we'll see in the coming videos why this dot product is really useful. See you then. Let's look at some interesting consequences of the dot product. And the first one that I want to look at is the consequence it has for the definition of the length of a vector. It turns out that because the way the dot product is defined, we can think of the length of the vector as the square root of the vector dotted with itself. And why does that make any sense? Well, if we think about what this is equal to, this dot product here is just u1 times u1, which is u1 squared, plus u2 times u2, which is u2 squared, plus all the way up to un times un, so un squared. So that just comes from the definition of a dot product. We take each of the components, we multiply them together, and we add them up. And we already said that this is how we are going to define the length of a vector. Remember, we did this in 2 dimensions where we used the Pythagorean theorem to find the length of a vector. In more dimensions, we just keep adding the squares of the components. However many more components we have, we square them and we add them underneath the square root. So that's the length of a vector, and so it makes sense that the square root of u dot u is the length of the vector. Also notice that, this is a pretty natural follow-up, but the length of a vector squared, that means, is equal to the vector dotted with itself. So we just squared both sides of this. Okay, that's pretty cool. What else? Well, the more interesting thing that happens is has to do with the angle between two vectors. So let's say this is u and this is v, and this is theta. Well, what if we did u minus v? We already talked about what u minus v is. It's the vector that points from v to u. Now we've drawn a triangle here. What we can do is we can use the law of cosines to help us figure out this angle in here, or to help us figure out this side, u minus v. So the law of cosines tells us that the length of the side we're trying to find, u minus v, so this is going all the way back to your geometry class, and you can look up the law of cosines if you don't remember it, but that length squared is equal to the length of one of the sides, that's u, the length of u squared, plus the length of v squared, minus the length of u times the length of v. So I know that these length symbols get really tedious, but I'm just going to keep going with them here. So minus the length of u times the length of v times the cosine of the angle between them. So this comes from the law of cosines. It's really just saying c squared is equal to a squared plus b squared minus ab cos theta. You might remember it better that way. But that's what we have. We have a side u minus v and a side u and a side v. Okay. So what we're going to do now is we're going to examine this side. So let's pull that side out and look at it separately. So we have the length of u minus v squared. Well, that's just u minus v dotted with u minus v. So let's do that. U minus v dotted with itself. And now there's some properties of dot products that I haven't told you about that are going to become useful here, like commutativity, but we'll see that in action. So u dot u, well, we just talked about that. That's the length of u squared. So let's write that as that. U dot u is the length of u squared. And then we have u dot, oh, I have dot products in there, sorry, that's a mistake. This should be u minus v, u minus v. So u dotted with minus v, that's minus, so let me write that on the side, minus u v, minus u dot v. And then we have minus v dot u, so that's minus v dot u, but like I just said, the dot product is commutative, so this becomes, when we add those two together, we just get minus 2 u dot v. So I hope that was relatively clear. We're just foiling this out with the dot product. Okay, so based on what we just talked about, that's minus 2 times u dot v. So just to be explicit, really explicit here, that was this u coming over here and this v coming this way. So I had to pause the video because my phone was ringing. But yeah, like I was saying, this u comes and multiplies that v. This v comes and multiplies that u. So we get minus 2 u dot v. Okay, and then finally the v dotted with itself, well, it's both negative, so that's going to be plus the length of v squared. This is just v dot v. It turns out to be. Okay, so this is what the left-hand side of the equation becomes. So why don't we substitute that in to this, the law of cosines, essentially, what we have. So this is u squared, the length of u squared, minus 2 u dot v, plus the length of v squared is equal to the length of u squared. So this is now the right-hand side of the equation from up there, plus the length of v squared minus the length of u times the length of v times the cosine of the angle between them. Okay, so now we get to do a lot of canceling here. So let's see. This and this are going to go away. We can subtract those from both sides. Those are going to go away. Oh, geez, I did something terribly wrong here. This is not the law of cosines. We need a minus 2. And that means we need a minus 2 down here. And then we could divide the minus 2 on both sides, though. So that's pretty cool. So sorry for forgetting that for the whole video. And what do we end up with after we do all that crazy cancellation? Well, we just end up with u dot v on this side is equal to the length of u times the length of v times the cosine of the angle between them. And now that is really cool because as long as we're given the vectors u and v, we could figure out what u dot v is based on the definition, sum up the products of the components. And then we can figure out the lengths. We know how to do that. We just take the square root of the sum of the square of the components. And then we have this cosine of theta, so we can solve for theta. And we can figure out the angle between two vectors just knowing what the two vectors are. So that's really cool. So in fact, well, remember that this proof came from the law of cosines, which only really works in 2 dimensions. We're talking about a triangle. So when we go to higher dimensions, we take it as a definition that the cosine of theta is equal to u dot v divided by the length of u times the length of v. So that just comes because we just divided by length of u, length of v. So notice two things happened here. One, we have an alternate definition for the dot product, or an alternate way to express the dot product. And also now we have a way to express the angle between two vectors in terms of the dot product. And that's really cool. So I hope this helps. I'll see you in the next video. Let's use what we and sum up the products of of the components. And then we can figure out the lengths. We know how to do that. We just take the square root of the sum of the square of the components. And then we have this cosine of theta, so we can solve for theta. And we can figure out the angle between two vectors just knowing what the two vectors are. So that's really cool. So in fact, of the times the cosine of the angle between them. And now that is really cool because as long as we're given the vectors u and v, we could figure out what u dot v is based on the definition, sum up the products of the components. And then we can figure out the lengths. We know how to do that. We just take the square root of the sum of the square of the components. And then we have this cosine of theta, so we can solve for theta. And we can figure out the angle between two vectors just knowing what the two vectors are. So that's really cool. So in fact, by the length of u times the length of v. So that just comes because we just divided by length of u, length of v. You might remember it better that that way. But that's what we have. We have a side u minus v and a side u and a side v. Okay. Let's use what we know about the dot product to find the angle between these two vectors. So what we're going to do is remember our little formula, which says that the cosine of the angle between two vectors is equal to u dot v divided by the length of u times the length of v. So if we want to find the angle between two vectors, we have to do just a few computations. We have to find the dot product, and then we have to find the length of each vector. So let's go through that. So the dot product of u and v, so u dot v, u dot v is equal to 2 times 1, that's 2, plus 1 times 1, that's 1, plus negative 2 times 1, that's just negative 2, or minus 2. So this comes out to be 1. So the dot product is 1. Let's do the length of u now and the length of v. So the length of u is equal to the square root of 2 squared plus 1 squared plus negative 2 squared. So 2 squared is 4, plus 1 squared is 1, plus negative 2 squared is 4, so plus 4. So this is the square root of 9 if we add those together, and the square root of 9 is just doing the. So now we have 1 squared, well that's just 1, plus 1 squared, well that's 1, plus 1 squared, that's 1. So this is the square root of 3. 1 on your calculator, just rounding.
Had result. Okay, let's try it.
a little bit, or truncating. This is approximately equal to 1.37 radians. And if your calculator is in degree mode, then that's approximately 78.9 degrees. Okay, so nothing too terribly difficult. We just got to compute the dot product, compute the length of the vectors, and everything falls into place. Okay, see you in the next video. In the last video, we learned the definition of the cosine between two vectors. In fact, we pretty much derived this. So we said the cosine of the angle between two vectors is u dot v divided by the length of u times the length of v. So let's see what we can determine about two vectors when they're perpendicular. So if two vectors are perpendicular, what we say is they're orthogonal. So that's the word we use for perpendicular vectors. And let's see what we can determine. So u and v here. So this angle, of course, is pi over 2, or 90 degrees. And what does that mean? Well, by our definition of the angle between two vectors, that means that the cosine of pi over 2 is equal to this dot product. And while I'm writing this, think about what is the cosine of pi over 2? What is that equal to? We know what it is, it's just a number, right? And what is they're orthogonal, so that's the word we use for perpendicular vectors. And let's see what we can determine. So u and v here. So this angle, of course, is pi over 2, or 90 degrees. And what does that mean? Well, by our definition of the angle between two vectors, that means that the cosine of pi over 2 is equal to this dot product. And while I'm writing this, think about what is the cosine of pi over 2? What is that equal to? We know what it is, it's just a number, right? Well, the cosine of pi over 2 is 0. So all three of these things are equal, and they're all equal to 0. Excuse me. So what does that tell us? Well, that tells us that u dot v must be equal to 0. So this implies that u dot v is equal to 0. And that's because the denominator here will never make this fraction 0. Okay, So if the vectors are orthogonal, then the dot product is 0. And in fact, that works in the other direction. If the dot product is 0, the vectors are orthogonal. So now we have a definition of orthogonal. Two vectors are orthogonal. So let me write this. Two vectors u and v are orthogonal if and only if. If you've never seen this before, this is shorthand notation for if and only if. Two vectors are u and v are orthogonal if and only if u dot v is equal to 0. So now we have a nice easy way to test if two vectors are orthogonal. So let's take a look at that. So let's take two easy vectors with just two components and see what happens. So let's say u is equal to -3, 4, and v is equal to 4, 3. Well, let's do their dot product really quickly. U dot v is equal to -3 times 4, -3 times 4, plus 4 times 3. Well, it's pretty clear this is -12 plus 12, so that's 0. So by definition, these two vectors are orthogonal. So let's take a look at what they look like if we were to graph them. So u is -3, so we'll go over 3 up 4, -3, 4. So it's kind of a rough sketch. And then v is +4 and up 3, so about there. And even though this is just a rough sketch, it seems pretty reasonable that these two vectors are orthogonal. That looks to be about 90 degrees in there. And we know for certain, because this dot product is 0, we know for certain that they are orthogonal. And just by the sketch, that kind of confirms in our mind, if we had any doubt, that they are indeed orthogonal. Okay, so this is the definition of orthogonal. I'll see you in the next video. In the last video, we learned sketch, they, that kind of confirms in our mind, if we had any doubt, that they are indeed orthogonal. Okay, so this is the definition of orthogonal. I'll see you in the next video. Okay, here we have a proof to do. We need to prove that the diagonals of a parallelogram are perpendicular if and only if the length of their sides are equal. Okay, so the first thing that I want to do is just get some intuition about what we're actually trying to prove and write a mathematical statement of what we're trying to prove. So kind of convert these words into math. So the first thing I'm going to do is just draw a parallelogram to see what's going on. So here are two vectors, u and v, and we know we can make a parallelogram out of them. So here's, well, let me switch to a thinner brush. So here's u and here is v. And we know we can make a parallelogram out of them, so let's do that. Oh, and I should tell you that I made these vectors exactly equal in length because it says that we want them to be equal in length. So I wanted to see what was going on with that. And now we know how to create the diagonals, right? If we do head to tail addition, we can get this main diagonal, and we know that that's u plus v. And then how do we get the other diagonal? Well, the other diagonal is just u minus v. So that is here. U minus v. We talked about that in vector subtraction. The vector pointing from the head of one vector to the head of the other is the vector is vector subtraction, essentially. Okay, so we have our two diagonals. Let's see if we can convert this statement into some math. So what we're trying to prove is that the diagonals u plus v are perpendicular, right? U plus v and u minus v, we're trying to prove that these are perpendicular. So we could say that their dot product is 0. So the diagonals are perpendicular. That's this statement. The diagonals are perpendicular if and only if the length of their sides are equal. So this is length of u is equal to length of v. Okay, so now we have a proof, and we need to go in both directions. So let's go forward first. Let's say assume too many m's. Assume that the dot product is 0. So assume that the vectors are, or sorry, that the diagonals are perpendicular or orthogonal. We're going to assume this, and now we need to prove that the lengths are equal. Okay, well, let's just see what happens through this equation if we expand it out. So that equation implies, what is the dot product expanded here? Well, we're going to have u dot u, which we know is the length of u squared, minus, and then we're going to get minus u dot v, so minus u dot v, plus v dot u, and then we're going to get minus the length of v squared, because this is just minus v dot v. Okay, the dot product is commutative, and so u dot v is the same thing as v dot u. So we have a minus v dot u dot v here and a plus u dot v, so those are going to cancel out. Oh, and I kind of made a mistake here. Sorry about that. This is an implication. The fact that this is equal to 0 implies that this statement is equal to 0. because all we did was expand it out, which in turn, let me switch colors here. Well, maybe not. Maybe I'll leave it where it was. Which in turn implies that the length of u squared minus the length of v squared, oops, I forgot my vector there, is equal to 0, which again implies that the length of u is equal to the length of u squared is equal to the length of v squared. Well, lengths of vectors are always positive, and so we could take the square root and not really worry about messing up this equality, because we're not going to need the negative part of the square root, because we know both of these lengths are positive. So we take the square root of both sides and we get exactly what we wanted, that the length of u is equal to the length of v. Okay, so we proved that if the diagonals are perpendicular, then their lengths must be equal. Let's go ahead and prove that if the lengths are equal, then the vectors must be perpendicular. So I'm just going to write this kind of backwards implies arrow just to indicate we're doing the other part of the proof now. So we're going to assume that the lengths are equal, and what we want to get to is that the vectors are perpendicular, or the diagonals are perpendicular. So we're going to assume this. Now this doesn't seem, it seems like, well, where do we go from here? How do we construct a proof out of just this equality? Well, what I would do is I would say, okay, consider the dot product of u plus v dotted with u minus v. So the dot product of the diagonals. Now we're not going to say that this is equal to 0. We can't do that. That's what we're trying to prove. But we can just see what comes out when we take this dot product. We know that that this dot product exists. We have two vectors. We can take their dot products. Okay, so let's do that. Well, this is equal to, that dot product is equal to, well, we already did this. It was the length of u squared minus the u dot v plus u dot v. I just commuted there. It would be v dot u, but I just commuted the two vectors. And then minus the length of v squared. And this is equal to the length of u squared minus the length of v squared. Since u is equal to v, we can substitute one in for the other, and we know, of course, that this is equal to 0. So we took the dot product and we found out that, yes, the dot product is equal to 0. So that's it. We're done with our proof. We proved that if the lengths are equal, the dot product is 0. We proved that if the dot product is 0, then the lengths are equal. Okay, and again, just one more time, when I say that the dot product is 0, what I'm implying by that, by definition, is that these two vectors are perpendicular, and of course, from the beginning of the video, those two vectors represent the diagonals. Okay, so that's a somewhat of an interesting proof. The diagonals of a parallelogram are only perpendicular if and only if the lengths of the sides are equal. Okay, see you in the next video. We already did this. It was the length of u squared minus the u dot v plus u dot v. I just commuted there. It would be v dot u, but I just commuted the two vectors. And then minus the length of v squared. And this is equal to the length of u squared minus the length of v squared. Since u is equal to v, we can substitute one in for the other, and we know, of course, that this is equal to 0. So we took the dot product, and we found out that, yes, the dot product is equal to 0. So that's it. We're done with our proof. We proved that if the lengths are equal, the dot product is 0. We proved that if the dot product is 0, then the lengths are equal. Okay, and again, just one more time, when I say that the dot product is 0, what I'm implying by that, by definition, is that these two vectors are perpendicular, and of course, from the beginning of the video, those two vectors represent the diagonals. Okay, so that's a somewhat of an interesting proof. The diagonals of a parallelogram are only perpendicular if and only if the lengths of the sides are equal. Okay, see you in the next video.
My name is Freya. I have been in the industry professionally for about 9 years at this point, maybe 10 years. I also used to be part of Future Games. I was in the class of 2010. I've been teaching future games since like after 2 years after that. I started teaching future games as well. I did mostly like C# courses and math courses, as well as some guest lectures. Otherwise, like professionally, I made a plugin a long time ago, release title. One thing mean that you're stupid. So we can interpret 2 as a vector. So I feel like there's a concept that is talked about very early on in your math course. Usually it's referred to as the number line. So you can imagine this like one-dimensional space. We can just move along this one line, right? And in the center, we can put the number 0, right? And then you can sort of imagine a space where these numbers are kind of put along this whole line, right? All right, so we have 1, 2, 3. So all integers are on these little notches. All right, cool. So this is a number line. It's like, I think it was like usually this, but I think it's an extremely kind of the center and negative number here, right? So whole numbers are integers, and then between those, you can have decimal numbers, right? So you have 0.5 here, so that's halfway between. That's very important numbers in terms of anything else. What is so usually, so 2 could be in which on this one dimension, right? So we could call this the one. We could represent them as just letters, right? So in this case, we want to do 3 minus 1, and then that gives us 2, right? So then we get the distance between these two numbers. So usually doing like subtracting is usually is 2. Is 50%. So what we're going to do if we multiply 2 by 0.5 is that it's going to be half as long, right? So that's going to have a value of 1 because 2 multiplied by 0.5 gives us 1. And the same thing is, but as far as first off, when we work in multiple dimensions, it's really useful to use colors. So let's but as far as I know, it was like it was an approximation of doing the inverse square root of something, and we used like kind of weird bit shenanigans that sort of only works with certain representations of numbers in binary. But yeah, I don't know too much of the history behind it except what I just said basically. But I'm sure there's a Wikipedia article or something you can go to. Okay, we've talked about one-dimensional numbers. One-dimensional vectors are usually not called one-dimensional vectors. Usually people just call them scalars. People call them floating point values in programming or decimal values. So I've sort of approached this in a non-conventional way. So don't call things one-dimensional vectors because you're going to confuse people. But the only reason I approached it this way is because all of these functions have direct analogies to the higher dimension vectors. So let's go to 2 dimensions. Let's just enter another world or something like that. So usually when we talk about dimensions, usually we have axes, right? Currently, we've only had one axis, like it's the x-axis usually. This is the number line. We only have the one axis where we have all the numbers, right? And if we want to represent a position here, all we need is one number. Unreal is also all right, so we have the vector A. The vector A has these values, right? And then we want to add to this. So again, when we were adding numbers, we sort of had a one-dimensional vector plus another one-dimensional vector, right? If we want to add 2-dimensional vectors, you would kind of get some number here, plus some number here, right? Because you have x and y coordinates, right? So you would have x, y, if you want to add two two-dimensional vectors together, right? Okay, so let's pick another vector. Let's say we want to do the vector here. So what are the coordinates of this vector? There we go, a question for class. How would we write the coordinates of this vector? It's always really awkward when you ask the class for like questions because it's usually obvious. and then like some people don't really want to answer anyway, and it's like, it's weird. I'm not going to do this again. This was a mistake. Okay, negative 1, 1, exactly. Because it's if we look at the x-axis here, this position on the x-axis lands at negative 1. Just like this position on the x-axis landed at 2, right? So now one thing that's nice about looking at it this way is that if you have some value like a plus b, this is actually equal to b plus a. This might seem like it's kind of trivial that, well, of course that's the case, right? Well, why would it not be? But remember that that's not the case for, like, if you have a minus b, that's not equal to b minus a, right? So it's not always the case that if you flip the values, you get the same result, right? So it's really important to like keep it in mind when things are, I always forget if it's commutative or which one is which. There are terms for this. Anyway, so if we look at this, if we think about what we did here, we had the vector a at the bottom, and then we added b to a, right? Because we added b here. So if we just look at the geometric interpretation of this, we should get the same point if we do b plus a, right? So if we try that, then we have the vector b. So now instead of moving b over here, we can move a over here, right? So if we put a here, we end up at the same point. It's the same result, regardless of what order we do this in, right? Commutative. Okay, people are confirming that it's called commutative. Good. Okay. Anyway, sometimes that's a useful term to know. Like it's the same thing for scalars. A multiplied by b is the same thing as b multiplied by a, but that doesn't always apply. In some cases, multiplication is not commutative. So for instance, if you're working with matrices or quaternions, then multiplying those is different depending on the order that you do it in. I think matrices are non-commutative. All right, any questions so far? Is this clear how things work? Was something a little weird, wonky? Then I guess just ask questions at any time. I'm always up for answering questions. So that's sort of how addition works, right? If we talk about, let's say, subtraction. Let's see, I should probably undo a bunch of arrows. All right, so as Steve is saying in the chat that I'm not supposed to read, subtraction is addition in the wrong direction. So just like we took one arrow, put it at the tip of the other arrow, subtraction is, again, like we talked about before, subtraction is the same thing as addition, but we negate one of them, right? And negate in this case, well, we were thinking about like one-dimensional numbers before, right? We have a value of 2, and then when negate it, we're going to get negative 2, right? And if we have negative 2 and negate that, we're going to get 2. So negation is basically we flip the arrow to the other side around the origin. So in 2 dimensions, it's exactly the same thing. We could do it like per component. We could think about like, what does it mean to negate the x-axis? Well, if we negate or if we negate the y component of this one, we're going to get this vector. And then we negate the x component, which used to be 2, and then it's going to flip to negative 2, right? But an easier way of thinking about it is you just flip the arrow to point in the opposite direction, right? So if we negate this vector, then we're going to get this vector, right? Which is the same thing as just negating these individually. So we could just copy those, move them over, and then we have -1 and -2, right? So now, if we want to subtract something, if we want to do b minus a, then we add what this is, right? Values. All of these concepts also generalize to 2D and any other numbers of. Okay, so we're going to talk about how to normalize a vector. Didn't quite get the normalization. So basically, if you have any vector, pick up any point on over here, then that's going to be a line from 0, right? If you want to normalize this vector, what that means is that you make the length 1. So what you get out of it is a vector pointing in the same direction, but it's got a length of 1, right? So it used to be this whole vector, but if you normalize it, it's going to shrink down into a length of 1. Or if you pick a vector that has a length that's smaller than 1, this vector is going to normalize into being longer all the way out here. So basically, you can sort of consider it to be a way from going from a point to an arrow that represents the direction to that point. Yeah. When do you usually need to normalize a vector? So the concept of a direction is really important. So say you have an object that is over here. Let's say maybe this is an enemy, like at this location. And then you want to know, let's say maybe the player is at 0. And you want to know what is the direction that you need to move in order to move towards the enemy. So if you are dealing with like physics or something, and you want to add the vector to move toward the enemy, then usually you want to move at a fixed rate in terms of speed, right? So what you usually do then is you normalize the vector between the player and the enemy, and then you have a normalized vector, which again, that's a direction usually in terms of terminology. And then once you have a normalized vector, if you multiply that by your speed or some value that represents how much you want to move in that direction, you can guarantee that that's going to be in, meters per second, or that distance is going to be in meters, because the length is 1, right? So that means that you get consistent movement in space. What's the difference between Unity's normalized method and normalized? Yeah, the dot normalize will modify the original one, whereas the other one returns a vector. Okay, did that make sense? So basically, pick any point. Normalizing it means you get the direction to that point. And a direction in this case, I'm using the word direction to be interchangeable with a vector with a length of 1, right? But it's still pointing towards that point, right? Like I mentioned before, one of the powerful things about having normalized vectors is that, let's see if I can undo a bunch of things. So if you have a direction like this, you can multiply a vector with a scalar, as in a a single value. So if you have a vector, again, usually when people say vector, they mean multiple components rather than one. But if you have a two-dimensional vector, you can multiply that by 2, for instance, or like some number. But if you have the normalized vector, so let's say we have our vector that's normalized. It's the same thing as this one. And then we multiply that by a value of 2. Let's pick 2. What that means is that the new vector we are getting out of this, that is going to be the direction along V right here, but the length of it is going to be 2. So this is kind of what is extremely useful about normalized vectors, because if you want to move like 2 units towards something, then having a normalized vector means that you can get a position that's exactly like some number away from some point. So if you normalize a vector, multiply it by a distance, then you're going to make the length of that vector the value you're multiplying it with. And it might seem like that's kind of trivial, but that's not the case with this vector, right? If you multiply this by 2, then the length of it is going to be like all the way over here, right? So the length of this is definitely not 2, right? It's way longer. So this is why normalized vectors are extremely useful, because of the fact that the length is 1. If we multiply weird behavior as soon as you hit that point. Okay, let's see. All right. I probably should have done code examples earlier, actually, because again, I like keeping things very pragmatic and practical. Okay, let's just do some of the things we've done here, just to show how it works, right? So I usually really like using onDrawGizmos because you can see it in the editor. You can very easily like draw lines and whatnot. So onDrawGizmos is a special function in Unity that is called in the editor, and you could optionally enable it in the game view as well, where you can like draw lines and whatever. So you can do stuff like gizmos.draw line, and then you can supply some positions, right? So we do something like that. Then we go back to Unity. We now draw a beautiful, tiny little white line, right? Cool.
That line is all gross and alien.
Oh, wow. I wonder if there's a vector graphics package you could get. Okay, so, all right, so draw a line, just a very simple one. But we probably want to be able to like supply some other points. Do I have to wrap onDrawGizmos in if Unity editor? I'm pretty sure that's going to get stripped for builds, but I could be wrong. Sometimes you use methods in there that are only in the editor namespaces and whatnot, but like if you use handles, for instance. But Gizmos, it kind of ignores that, I'm pretty sure. Yeah, I'm pretty sure you don't need to strip it. It's not gonna, like, maybe the code in here will be part of the assembly. I'm not sure, but at the very least, it's not gonna get called, regardless. Yeah, bye now. Bye. Okay. All right, so we probably want to be able to pass a vector into this, or a point, or whatever, right? So instead of just hard coding it here, we can add a property, or in my case, I'm just gonna pass in a transform because it's easier to move it around. Let's call it point transform. Let's make a new game object. Actually, because since we're drawing all of this in world space, we can just use this transform. All right. Let's pass point into there. All right, so now we're drawing a line between 0 and this transform, right? So now we're basically just taking the position of this transform and we're drawing a line to it, right? So again, we can think of this as the two normal lines we had, where this is the origin, and then we have the x-axis and the y-axis right here. Oh, you couldn't hear the Discord? You should have been. It might have been a lower volume. So, all right. So now we have the point, right? So now let's say we want to get the direction to this point, because we have been talking a lot about directions, right? So let's get that. So direction to points. So in this case, because it's originating from 0, and we just want the direction to this arrow, then all we need to do is normalize that point, right? And Unity has a bunch of built-in functions. You can do point.normalized, and that's going to return a normalized version of this point, right? Yeah, so now we have the direction to the point. And again, I'm using the word direction to mean a vector of length 1, which is sometimes also called a unit vector, a normalized vector. Like, it has a bunch of terms, but usually when I use the word direction, I mean a normalized vector, just to like clarify. Okay, so if we draw that instead, and then go back to Unity, now this line always has a length of 1, right? Doesn't matter how far away the transform is, but the length of it is also 1. Even if it's shorter or longer, it's going to normalize it to always be unit length. So it's sort of tracing the outline of what's called a unit circle. So the unit circle is just all the points of the vectors that have a length of 1. So it's this circle right here, right? So now we have a direction, right? What if you set the transform to 0? So probably now it gets very sad because I'm pretty sure normalized, it looks like it's just returning a 0 vector. So now the quote-unquote direction that this returns is going to be 0. So it's trying to draw a line from 0 to 0. So speaking about that, this is a very good case where when you have something like this, this is actually division by 0, like technically. We're going to get into how to calculate the length, or how to calculate the normalized vectors later. But this is actually division by 0. And something that is kind of beautiful in mathematics is that anytime you are dividing by 0, I think this is like so mind-blowing, but like every time you're dividing by 0 in some equation, that is kind of the math talking back to you, saying that like, hey, this is a weird case. You need to handle this case. Something is happening here, and you need to think about what do you actually want to happen in this case. Because it's kind of telling you that there is a degenerate case, or a case that you cannot calculate, because division by 0 is undefined. So whenever you have an equation where there is a divide line, think about if the denominator can ever be 0. If it can be 0, figure out what that means, right? Like, when would this be 0? Anyway, okay, so now we're just drawing the normalized version of this vector. Do you have a course at Udemy? No, but I have my YouTube channel, which is free, so you don't have to pay for it. All right. Cool. Okay, so let's talk about the length, because we've sort of mentioned the length a lot when it comes to normalizing things. We probably should have talked about No.1, even if it's shorter. When I use the word direction, I mean a normalized vector. Just to like clarify. Okay, so if we draw that instead, and then go back. Clarify. Okay, so if we draw that instead, and then go back to Unity, now this line always has a length of 1. Okay, so let's talk about the length, because we've sort of mentioned the length a lot when it comes to normalizing things. We probably should have talked about length before normalization, but you know what? That's okay. All right, so let's talk about length. How do you get the length of the vector, right? I might be skipping ahead, but when you say the vector2 dot normalize divides by 0, where does it do that? You are sort of skipping ahead. I'll get to that. But it technically, Unity's vector2 dot normalize handles that case and just returns a 0 vector instead of, you know, crapping out and not knowing what to do. You could sort of make a normalize function that just throws an exception, which might be useful. But Unity's normalize just returns a 0 vector. Oh, a 0 vector is just a vector with components at 0. So all of the components are 0, sometimes called a 0 vector. Yeah. Okay. So we've talked about normalization, but not how to calculate it. Like how do you normalize a vector? Like how do you go from this to whatever the heck these coordinates are, right? All right. So if there is I don't know if we should use this vector. Let's do another vector. Let's do this one. What a vector. It's a little curved, but pretend it's not. All right, so let's see. What is this vector? So we have x coordinate, we have -2. Y coordinate, we have 3, right? So this is our vector. So now I want to know the length of this. Like, how do we do that? So now this is going to get into the hacking Pythagorean theorem, right? Because if you think about it, if you want to get the length of this, you can sort of imagine a triangle here. And this is a right angle triangle. And this is something that is taught in math class. So if you remember how to get the length of the hypotenuse, then you know how to get the length of a vector, right? So basically what we need to do then is we take the x component, square that, and then we add the y component and square that. And then we take the square root of all of this. There we go. That's the Pythagorean theorem. That's how you get the hypotenuse of a right angle triangle, right? But this is how you get the length of a vector, right? Is that clear, by the way? We haven't talked about like exponents or what it means for something to be squared or talked about square roots, but I'm guessing we don't need to talk about that, or but if not, let me know. We can talk about it. Okay, so this is basically how you get the length of a vector. All right, that's it, I think. So now we've been talking about actually do the full equation, but for anything like it works for two-dimensional length. You know, I actually have a cold right now, so this is like canonically kind of more accurate, but sorry. Sometimes my backwards writing doesn't work out. Okay, cool. So now we have that, right? Now we can actually do that math. So if we want to get the length of this one, we can just do that, right? So that's -2 times -2 plus 3 times 3. And then we do the square root of that. This is not a good looking square root. Where's my good color? There we go. So then we can just run these numbers, right? So, all right, we do square root of -2 times -2. Pretty sure that's 4. So it's going to be 4 plus 3 times 3, that would be 9. So 4 plus 9, which is, oh god, that's 13, I think. Like, again, I'm really bad at doing math in my head. Pretty sure that's 13. All right, so it's no longer really tied to the x, or that becomes 30 later. And it turns out it's 3 point equal to 3.6. Oh, sorry, maybe we'll do it in blue. Why not? Cool. So that's how you get the length. So now, what this value represents is the length of this right here, right? The full length of this vector turns out to be 3.6 something something, right? So now we know the length of it, right? Cool. That's how we do it. If you want to get the, if you want to do this in practice, you almost never write this formula yourself. So if you go to Unity, if you want to get the length of the point or the vector, again, length is a scalar. It's just a single value. So the length of this one would be point.magnitude, because again, magnitude and length, same thing. So this is how you get the length. Sometimes it can be useful to calculate the length manually, because sometimes you want both the length and the normalized vector, and in that case, calculating things manually can be really useful. Cool. Everything clear so far? How to get the length of a vector. So now we've just talked about how to get the length, but not how to get the direction or sign, and not how to get the distance. Okay, let's do the distance. So the distance, now that we know how to get the length of something, now if we get the difference vector, or the displacement between two vectors, let's say we want to get this vector between these two right here, then this vector, this would be, we don't have names for these. Let's call it A and V. There we go. So in this case, this vector right here would be A minus V, right? A minus V. So now we have the difference between these 2 points, right? So if we want to get the length, or the distance between these two vectors, all we need to do is get the length of this vector. Because that, if we know how to get the length of this, then we now know the distance between these 2 points. And in this case, it also doesn't actually matter if we do V minus A or A minus V, because if we're just interested in the distance is always positive, so it doesn't matter which order we do this in. So if you want to get the distance between 2 points, previously we did the absolute value, because that's how we did the distance in 1 dimension. Actually, we never call it length. Anyway, so this is how you do the length. So we can basically just replace this by calling it length instead, right? So now we have we can get the length of this one, and the way to get the length is this one right here, right? There we go. Cool. All right. So basically, this is how you get the length. If you want to get the distance between 2 points, then you subtract the points, one subtracted by the other, and then you get the length of that vector, and then you get a distance. So there is a slight difference in terms of interpretation between distance and length. So distance usually is between 2 points, and length is usually the length of 1 point, or the length of the vector that represents that 1 point. So when we want to get the distance between this point and this point, we first subtract them from each other to get the difference vector, and then we check the length of that difference vector. All right, so now we have a way of getting the length. We have a way of getting the distance. Have we clarified that the resulting blue vector is still centered on the origin? We talked about that, yeah. vectors don't have a root and a tip. It's only the vector data itself, right? So we talked about that when we talked about subtraction, that if you want to draw it at its origin, it would be this vector, right? Length magnitude is of the vector, distance is between two vectors. Generally, yeah. So when you talk about distance, that's a special case where you want to know how long is the vector that is the displacement between these 2 points, basically. So when you talk about distance, again, distance has an input of 2 points usually. And then you get the difference of those 2 points and get the length of that. If you want to know the length of something, it's just one input, right? So that's just the length of one vector. Yeah, of course, there are built-in helpers for this. You don't have to do it manually. So if you want to know the distance between 2 points, you can use vector2.distance from A to B, or db null, I guess. So this would give you the distance, but you can do it the other way around too. You could do A minus B dot magnitude, for instance. This would also give you the distance. It's the same thing, right? All right, or you could do the manual way if you want to, of like doing like A minus B, like A dot X minus B dot X, and then you square that, and then you add the same thing but for the Y component, and then you do the square root of all of that. So this is the same thing. Like this is also a way you can get the magnitude or the distance between 2 points, right? Yeah, just different levels of abstraction, I guess. How to apply it in practice? Well, we could make 2 points. All right, let's make A green, B red. Now we have 2 points, right? What a good pair of points. Okay, let's say we want to know the distance between these two, right? First we need the actual points because we only have transforms here. So it would be, oh, I need to probably assign them in the inspector. Dude, there we go. So now we have, let's see, we just call them A. So that's going to be A transform dot position. Then we do the same thing for B. So now we have the 2 points A and B, and again we can draw lines to make sure that this is working. Right, I'm not using my library. Gizmos. Draw line from A to B. There we go. Cool. So now there should be a line between these 2 points. So we can move them around, and we now have, yeah, this. What a good line, right? But we want to know the distance of that. So if we want to know the distance, I guess we can print it in the inspector or something. So if we want to know the distance, then again, we can use everything we typed here, right? So we can do vector2.distance. And now we should set this value right here. It might be hard to see it in the inspector, but there's a little value there. There's updating. Now it's 0.45. Now it's 1.9 and so forth. So now we actually have the distance right there. Yeah. So that's how you use it in practice. And again, the distance value is going to be exactly the same thing if we do A minus B dot magnitude. So we can compile this. It's going to work. And yeah, still have the same distance. Any other questions before lunch? Any thoughts? How to make a game like Angry Birds? I can't answer that. That's a very long question and a whole production pipeline. Start doing things. That's how we make games. Generally speaking, no one's going to get mad at you for doing a minus b dot magnitude instead of vector 2 dot distance. I don't think so. I mean, the first one might be slightly more esoteric because you sort of need to know the underlying math for that to be readable. But I think most people should know about that. It's a very important concept. Like vector 2 dot distance, the nice thing about using that one is that you're being very explicit that you literally want the distance between 2 points. If you use the a minus b dot magnitude, it's a little unclear. Like you get the length of the difference between these two, but like, is that interpreted as a distance? Now we have 2 points, right? First, we need the actual points because we only have transforms here. So it would be, oh, I need to probably assign them in the inspector. Dude, there we go. So now we have, let's see, we just call them A. So that's going to be A transform dot position. Then we do the same thing for B. So now we have the 2 points A and B. And again, we can draw lines to make sure that this is working. Right, I'm not using my library. Gizmos. Draw line from A to B. There we go. Cool. So now there should be a line between these 2 points. So we can move them around and we now have, yeah, this, what a good line, right? But we want to know the distance of that. So if we want to know the distance, I guess we can print it in the inspector or something. So if we want to know the distance, then again, we can use everything we typed here, right? So we can do vector 2 dot distance. And now we should set this value right here. It might be hard to see it in the inspector. Now we should So if we want to know the distance, then again, we can use everything we typed here, right? So we can do vector 2 dot distance. And now we should set this value right here. It might be hard to see it in the inspector, but there's a little value there. There's updating. Now it's 0.45. Now it's 1.9 and so forth. So now we actually have the distance right there. Yeah. So that's how you use it in practice. And again, the distance value is going to be exactly the same thing if we do a minus b dot magnitude. So we can compile this. It's going to work. And yeah, still have the same distance. Any other questions before lunch? Any thoughts?